I did that because, remember the Markov blanket principle? We don't have to consider anything outside of our Markov blanket. We just have to know, basically, it's the probability of this node, given its parents, times the probabilities of its children, given their parents, and that represents the true distribution of the nodes. That's expressed in this equation here. And notice this upper equation is normalized. If we don't normalize it, then it's a very simple thing. It's just the conditional probability of the node multiplied by the conditional probability of its children. And this is a true proportion. Now you might say, what the heck good is a proportion, right? If you know something is proportional to something else, but you don't know by what factor, then you might say you know nothing because you don't know the factor. But there's only two possibilities that B can take. It's either true or it's false. So if we can get the proportion of true and the proportion of false, then we can use those two values to normalize it and arrive at the true answer. Is that too much reasoning for one mouthful, or is that digestible? Okay, so really all we have to do here is take this value, 2/3, and multiply it by this value, 1/2. And that is not the true probability that B is true, but it is proportional to it. Okay. So that's what we've done here is we've computed 2/3 times 1/2. That's proportional to the probability that B is true. Let's do the opposite one. What are the odds that B is false? Given those two conditions, A is true and C is true. Well, they're those. Multiply the other two numbers together. Now that we know the proportional probabilities of B, how do we get the true probabilities? Simple. Why does it do that? Stop that. We normalize. Okay, so basically we sum them up. What's going here? We normalize sum to 1 and we get 0.75. I don't think I worked through that math very obviously. 2/3. Let's do that. 2/3 times 1/2 is 1/3. So there's a 1/3 chance B is true. There's a proportional to 1/3 chance B is true. Okay? 1/3 times 1/3. There's a 0.1111 chance that B is false. Or there's something proportional to that. If we sum them up, we get 0.4 bar. That's how much total probability we have to work with. So 0.3 bar divided by 0.4 bar. Now I'm normalizing, and I get 0.75. So there's a 0.75 chance that B is true given that A and C are both true. Okay. And we can repeat the process for that second question. It's no different, and we get another number there. But I think you can look at this and see that that's the only hard question to ask about this whole network. In fact, that's what I'm saying is, the question I just answered is the hardest question you could possibly answer about this network, right? Because if you were to ask, what's the probability that A is true, given that we know nothing? So if you clamp nothing and just run on it, it darn well better come out to 2/5, right? Because we say so. It depends on nothing. What if we clamp B to be true? Then what's the probability that A is true? Well, it's going to be, we assume A is true, so we got 2/5, and multiply it by, let's see, by the conditional probability that B is true. Would that be by 2/3? I feel like I'm making a mistake right now and I can't understand why. Okay, so we just have to set A to be true and calculate the probability of that occurring. We set A to be false, calculate the probability of that occurring, normalize them. Now we've got the probability of A being true. Okay, if B is unknown, then the probability of A is definitely 2/5. Doesn't matter what C is. You can clamp C to be true, you can clamp C to be false. A will not be affected by that except to the extent that B is affected by it. Okay, so yeah. Okay, now let us suppose that B is, let's suppose we clamp A to be true and we clamp B to be true. What's the probability that C is true? No, it's easier than that. We're overthinking it. If B is clamped to be true, the probability that C is true is 1/2. Yeah. Because there are no children from which we can infer more knowledge about C. Okay, therefore, it is affected only by its parents. And I mean, there's no other knowledge in the universe that could be used to infer C. Therefore, all we've got is its conditional probability. Okay, I'm going to say that's probably the easiest one to necessarily get right. So, very clear that if B is clamped to be true, no matter what A is, that clamping blocks A from influencing C, right? And if B is clamped to be true, the probability of C is 1/2, and nothing else could be the case. And if B is false, probability of C is 1/3, and nothing else could be the case. Okay, well now let us suppose we do Gibbs sampling. We should get those values, we know that, but why should we get those values? Because look what we do with Gibbs sampling. What's this one? Okay. Let Z be a vector of size V. Okay, a bunch of values. Essentially what we're going to do is we're going to temporarily set the value of n to V sub I. So let's suppose we're sampling node C here. And we're going to try to figure out, is C true or is it false? Well, if we set it to true, I need to define my conditions. I'm assuming B is true now. And I'm going to ask the question, what should C be? Okay. Every time I sample the nodes, if I sample B, what number is going to come out? 1, true. 1, however you represent true. Because remember, I clamped a true to B. So if I start sampling B, it shouldn't do anything. It should just return 1. It's clamped. You should have a line of code in your code somewhere that says, if this value is observed, just return the observed value, because I already know it. There's no sense in saying, what's your value? I already know what it is. I can see it. Okay, so every time you sample node B, you get a true. Every time you sample node A, you get something. But I don't care because I know it's not going to affect node C. Every time I sample node C, here's what happens. I temporarily set the value of n to V, Vi. In other words, I'm going to set C to either be true or false. And then I'm going to measure the conditional probability. So I'm going to ask node C, what's the probability that that value you have actually would occur? And where do I get that? This is it. It's going to say, oh, well, with 1/2 chance I was true. Okay. Then for each child, there aren't any, right? So I don't do anything. Now I normalize it. What's going to happen when you normalize it? Nothing, because what's the conditional probability that C is false? Aha, I got you. It's not 1/3. It's 1/2, because this one is the probability that B is true, C is true given that B is true. This one is the probability that C is true given that B is false. That's not the same as the probability that C is false given that B is true. Did you catch that? Okay, so when you're debugging, pay a lot of attention to that. If there's a 1/2 probability that it's true, there is a 1/2 probability that it is false. So when you visit both of the values, see here, this for I from 0 to V minus 1, that's saying visit all possible values for the node. Visit false, visit true. And for both of them, compute the conditional probability, so it'll be 1/2 in both cases. Right here, we normalize it, so it sums to 1. What's 1/2 plus 1/2? 1. Therefore, we draw a new value for it from those probabilities. With 50-50 chance, we're going to set it to be either true or false. So, given that you sample it for a darn long time, on average, how often is C going to be true? 50% of the time. Therefore, can you see that that number is exactly what came out? And if it doesn't, you should be able to find the bug in your code, because by darn, you're drawing from a 50-50 chance, 50% of them should be true. Otherwise, you're not drawing from a distribution right. Okay? Now we need to do the more complex version and show that if we clamp A and C to be true and you keep drawing from B according to Gibbs sampling, you should get not any of those values. You should get 75% of the time B comes out to be true. Let's see if we can see why that happens with Gibbs sampling. It happens because let Z be a vector of size V for I from 0 to V minus 1. In other words, try false and try true. Okay? Remember, we're sampling the B node here. Temporarily set the value of n to V. So temporarily set B to be true. Let's do the true first, okay? And remember, A and C are clamped to be true. Zi is the conditional probability of Vi. So in other words, what's the conditional probability of true here? 2/3. Okay. For each child node, there's only one of them, happens to be this one, multiply by its conditional probability. What's the conditional probability that C is true given that B is true? And why do I do given that B is true? Because I have temporarily set B to be true, right? So for right now, B is outputting the value true. So I'm going to basically take 2/3 times 1/2. Okay. Then, if we look at Gibbs sampling again, now we continue on with the loop. Now we temporarily set the value of n to false, right? So B has now become false. And now that B is false, we're going to run through here. We're going to say Zi is the conditional probability of Vi. In other words, what's the conditional probability that B would be false given that A is true? It's 3/7, because we say so. Then we're going to visit for each child. There's only one of them. And we're going to say multiply that by the conditional probability of W, which is the probability that C is true given that B is false. Because B is now set to false, and C, we're asking what's the probability that's true. It will be 1/3. Why do we ask if it's true instead of false? Because it is true, because I clamped it to true. I said so, and it is. Therefore, I don't have to check the false case. Okay? So I multiply those numbers together, and then notice right here I normalize them and draw a new value from those probabilities. What are the probabilities going to be? It should say with 0.75% chance make B true, because those numbers I did are the exact same things I did right here, right? I ended up multiplying 2/3 times 1/2, and I multiplied 1/3 times 1/3, and I normalized, and I got 0.75. So at this stage in the Gibbs sampling, right after you normalize the values so they sum to 1, B should have a 0.75% chance of being true, and so with 0.75% chance you're going to draw true for B. So can you see that this little algorithm does what we did by exact inference? This little algorithm will draw the correct probabilities. Therefore, the thing does work. Okay. So if you're banging your head against why isn't it putting out the right values, I hope you can pound through that and it should put out the right values. Now, next you get to the metropolis case where there's this algorithm I gave you. It looks kind of complicated, but really it's not. Ultimately, the whole metropolis algorithm comes down to just this one line. And this is the whole key behind metropolis. You're saying, pick a random value and then either accept or reject it. We're either going to stay where we're at or go to the new value with that probability, E divided by F. And if you implement that line correctly, I'm pretty sure the whole thing's going to work because metropolis does work. I'm not going to take the time to go through a proof of it with you, so this is a matter of just kind of be a little bit careful and trust it will work. And if it doesn't, then I guess you're going to have to just hunt your bugs on this one. It would take more of a class than I have time to give to derive metropolis, but it does work. Good enough? here's some gotchas to watch out for. When I say temporarily set the value of this node to S, you see how Metropolis looks a whole lot like Gibbs sampling? It's almost the same thing. I don't quite, oh, I do say restore it right here. I don't mention when to restore it in the Gibbs sampling version. Did I pass it? No, right here. You kind of restore it right at the end of this loop. I should have said restore right there. But at the very end, we draw a new value for it anyway, so actually it doesn't matter. So never mind. The algorithm's just fine. Forget what I just said. Okay. What else can I say to make sure that you can do this without hitting any bugs? Kind of at a loss. I think you guys just got to go do it, and I think it should just work. The sooner you do it, the sooner you can confront me with your issues, and I can help you solve them, though, so don't wait till the last minute, please. Okay. Any other questions about that and how to make it work? All right. Let's talk about rejection sampling really fast. Almost done here. One of the things you need in order to use Metropolis, so let's suppose this is your distribution, and you're trying to draw values from this crazy wonky distribution. Well, the way it works is you have a point where you are at, your current location, and you're going to actually draw a value from a normal distribution. That's a terrible normal distribution. That's even worse. Hey, you can catch the last minute. Okay, so we're going to add a Gaussian value to the location we're at, and then with some probability we're going to accept and some probability we're going to reject it. What should be the deviation of this normal distribution that you draw from? The little one in this case. It turns out it does matter, but it also turns out it doesn't matter too much. The red one, that's what I'm saying. So here's the deal. It better be kind of wide enough that you can jump around and sample the outer distribution. Does that make sense? But it also shouldn't be so big that you're jumping way the heck out there. How do you find a good value? I don't know. You play with it until you get good results. That's kind of what it comes down to. It would be great if the deviation of your normal distribution was kind of approximately close to the deviation of the distribution you're trying to sample. But of course, if you knew that, then you wouldn't be trying to sample it. And so thus we face the catch-22 of the universe. You have to kind of guess, and you have to be close enough that a lot of samples will get you within there a lot. And then you can kind of start to figure out what the deviation is. And then it turns out you can even adjust the deviation of your Gaussian distribution if you want to. So you can dynamically tune it, and that does work. But you have to be close enough to get a few good samples to even let the dynamic tuning start working. And you also have to throw out enough burning iterations so that you're not changing too many things while it's trying to converge. So yeah, there's a lot of complexity there. Suffice it to say, for this assignment, I'm pretty sure if you use a deviation of 1, it's going to just work. But you can adjust your deviation a little bit. What can happen with Metropolis, and this throws people off sometimes, is suppose you have a distribution that looks like this. Oops. Oh, sorry, I'm almost out of time. So. And you use a Gaussian distribution that has a width that looks kind of like this. Will it work? What will actually happen is you'll jump around sampling this place, and you get a lot of samples over here, and you might not get any samples over here in this part of the distribution, right? Solution is you need a bigger deviation on the Gaussian you're using to sample it from. In reality, this does, or in theory, this actually does work because there is some non-zero probability you'll accidentally jump way over here and get this and pick up these samples. It turns out, though, that it would take you sampling for half of eternity before it actually happens. So Metropolis is provably correct. You can prove that the distribution it spits out will follow the true distribution given infinity samples. It's just that you usually want it in less than infinity samples. And so in order to get that, you need the deviation to be enough that you're going to, with some probability, sample all the different parts of it. And be aware of that. Okay, well, I'm out of time, so thanks for coming and see you next time.